All right, we are finally past day 22, and we are now ready to start on day 23 of Advent of Code 2022. Let's just dive right in. Unstable diffusion. You enter a large crater of gray dirt where the grove is supposed to be. All around you, plants you imagine were expected to be full of fruit are instead withered and broken. A large group of elves have formed in the middle of the grove. But this volcano has been dormant for months. Without ash, the fruit can't grow. You look up to see a massive snow-capped mountain towering over you. It's not like there are other active volcanoes here. We've looked everywhere. But our scanners show active magma flows. Clearly it's going somewhere. They finally notice you at the edge of the grove, your pack almost overflowing from the random star fruit you've been collecting. Behind you, elephants and monkeys explore the grove, looking concerned. Then the elves recognize the ash cloud slowly spreading above your recent detour. Did you just... Before any of them can form a complete question, another elf speaks up. Okay, new plan. We have almost enough fruit already, and the ash from the plume should spread here eventually. If we quickly plant new seedlings now, we can still make it to the extraction point. Spread out! The elves reach into their pack and pull out a tiny plant. The plants rely on important nutrients from the ash, so they can't be planted too close together. There isn't enough time to let the elves figure out where to plant the seedlings themselves. You quickly scan the grove, this is your puzzle input, and note their positions, for example. Then we have a map here with some dots and some pound signs and stuff. The scan shows elves. The scans show elves, pound signs, and empty ground dots. Outside your scan, more empty ground extends a long way in every direction. The scan is oriented so that north is up. Orthogonal directions are written north, south, west, and east, while diagonal directions are written NE, NW, SE, and SW. The elves follow a time-consuming process to figure out where they should each go. You can speed up this process considerably. The process consists of some number of rounds during which elves alternate between considering where to move and actually moving. During the first half of each round, each elf considers the 8 positions adjacent to themselves. During the first half of each round, each elf considers the 8 positions adjacent to themselves. If no other elves are in one of those 8 positions, the elf does nothing during this round. Otherwise, the elf looks in each of 4 directions in the following order and proposes moving 1 step in the first valid direction. If there's no elf in north, northeast, or northwest adjacent positions, the elf proposes moving north 1 step. And we have the same thing for south, southeast, and southwest. And then west, northwest, and southwest, and finally east, northeast, and south. And finally east, northeast, and southeast adjacent positions. After each elf has had a chance to propose a move, the second half of the round can begin. Simultaneously, each elf moves to their proposed destination tile if they were the only elf to propose moving to that position. If 2 or more elves propose moving to the same position, none of those elves move. Finally, at the end of the round, the first direction the elves considered is moved to the end of the list of directions. For example, during the second round, the elves would try proposing a move to the south first, then west, then east, and then north. In the third round, the elves would first consider west, then east, then north, then south. As a smaller example, consider just these 5 elves. The northernmost 2 elves and southernmost 2 elves all propose moving north, while the middle elf cannot move north and proposes moving south. The middle elf proposes the same destination as the southwest elf, so neither of them move, but the other 3 do. Next, the northernmost 2 elves and the southernmost elf all propose moving south. Of the remaining middle 2 elves, the west one cannot move south and proposes moving west, while the east one cannot move south or west and proposes moving east. All 5 elves succeed in moving to their proposed positions. Finally, the southernmost 2 elves choose not to move at all. Of the remaining 3 elves, the west one proposes moving west, the east one proposes moving east, and the middle one proposes moving north. All 3 succeed in moving. At this point, no elves need to move, so the process ends. The larger example above proceeds as follows. And then we can see how the map evolves. First the initial state, end of round 1, end of round 2, end of round 3, end of round 4, and so on. To make sure they're on the right track, the elves like to check after round 10 that they're making good progress toward covering enough ground. To do this, count the number of empty ground tiles contained by the smallest rectangle that contains every elf. The edges of the rectangle should be aligned to the north, south, east, west directions. The elves do not have patience to calculate arbitrary rectangles. In the above example, that rectangle is, as we can see right here. In this region, the number of empty ground tiles is 110. Simulate the elves' process and find the smallest rectangle that contains the elves after 10 rounds. How many empty ground tiles does that rectangle contain? Your puzzle ends... Yeah, that... Blah, 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 yeah. So the basic idea here is to parse the map, figure out where all the elves are, implement the rules for moving, and keep doing that until nothing changes. And once we're there, we find the maximum and minimum coordinates, use those to get the rectangle, and multiply them to get how many squares there are, and subtract how many elves we have. And that's it. So let's take a look at how we do that. Okay. So first of all, we define all the different directions that we are going to need, because that is probably going to be handy in a dictionary, so that we can look up from the name of the direction to the vector that we need to apply to move in that direction. Then we create a list of all the directions that we have, and then we proceed to part 1. So we get all the lines, we create a set that holds all the elves. Then we enumerate the lines and the characters in each line and find all the elves, and we add them to the set. Then we create this preferences list. Yeah, we create this preferences list. So the first the first element in the list is this 3 tuple right here, which is what we're looking in those directions, and if they are all free, we move to the first one in the list. This is just like it says in the instructions. And then we have those 4 because remember we needed to change the order. For each round, we changed the order of preferences there. So we put it in a list so we can move it around, or so we can change a pointer to them. Okay, so we have a round counter right here, and then we do round, which is pretty straightforward. Just following the instructions here. There's not a lot of interesting stuff here going on really. It takes the elves and the preferences and creates a copy of the elves. Don't remember why I do that, but that was probably useful. So for each elf, we let's see. All right, so get neighbor here is the first thing that actually does anything. So it takes all of the different directions and returns all of the neighbors of this given elf in all of those different directions. And if yeah, right, okay. So the first thing we do here is if we look at the rules from the puzzle. Okay. So you can see here, during the first half of each round, each elf considers the 8 positions adjacent to themselves. If there aren't any, they don't do anything. That is what we have right here. If the set of all of the neighbor spots, we AND that with elves, And if that's an empty set, then we're good to go. Then that elf doesn't need to move. If, however, one of the spots are taken, that means that we have to try to decide which way to move. And to do that, we look at the preferences list. So we see if there's any overlap by taking if we look at the neighbors in those directions. So first we look north, northeast, northwest, and that's what this line does right here. And if there isn't any overlap, that means that this move is now a possibility. So we store that move in a set. And then we proceed to the next elf, and we go through all the same things again, and we end up with a whole bunch of moves. Okay, so we create another couple of sets, one for all of the destinations, and one for the ones that we find that are invalid. So the move set contains tuples that contain elves and their new proposed position, which is in this direction right here. So we go through all of those moves, which gives us elves and destinations. If that destination is in all destinations, then it is invalid, and we add it to the invalid list, and that's it. We continue. If it's not in all destinations already, we add it to all destinations. So once we're done with this loop, the first time we see a destination, we don't consider it invalid, but the second time we do, we add it to invalid, and we don't add the second one. But we still need to go and remove whatever elf was already intending to go into that square. So again, we go through all the moves, and if the destination in that move is an invalid destination, then we continue. Then we go to the next move. If it is not in the invalid destination, we remove the elf from its current position and add the new position. We do that for all the moves, and eventually we end up with a new set of elves in their new positions, and then we shuffle the preferences around and we return. And we just keep doing that until we've completed a set number of rounds, and then we calculate the minimum and maximum coordinates. We multiply them, and then we subtract how many elves there are, and that gives us our answer. I got it over here. Okay, that should give us part 1. It does. I know that it does. There we go. Okay. So part 2. It seems you're on the right track. Finish simulating the process and figure out where the elves need to go. How many rounds did you save them? In the example above, the first round where no elf moved was round 20. Figure out where the elves need to go. What is the number of the first round where no elf moves? Okay, so we can recycle most of the code for this one. So we still do the rounds and all in the same way, and blah, 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 blah. And whoops. Yeah, I did some copy and pasting here, as you can see. I should clean it up later, but it's handy now that we have to look at it. Do the exact same thing again. You get the map, we find all the elves, we create the preferences and create the rounds and the round counter, and this loop is just a little different. So we go through the do round. So we do the round and we just keep doing that. And if the new elves set is equal to the old elves set, that means that nothing changed. And then we return the round counter, and that's it, actually. And that's probably why I added this this line right here. So I created a copy of the elves so I could return it instead of just changing it in place, which I imagine I did for the initial party. So yeah, that's it, actually. You can see I got the right answer here, and that's it. So day 23, quite a lot easier than day 22. Yeah, there you have it. That was day 23. Nice and easy. Okay, there you have it. All right, there you have it. That was it. That was day 23. I hope this was helpful. If you have any comments or suggestions, you leave them below. Otherwise, you like and subscribe, and I will see you in the next video. Bye.